Welcome back. In this section, we'll be introducing a new group of functions called the exponential functions. They all have this form. F of x is some constant times some base to the power of x. And we have some restrictions on those constants, c and a. The restrictions are there so that we have a function that's not a constant function. That's part of it. That's why we have the restriction that c can't be 0 and a can't be 1. Because if c were 0, then this whole function would just be the constant function f of x is equal to 0. And we also have that a can't be 1 for a similar reason. If a were 1, 1 to the power of x is just 1. So this would be the same thing as just our constant function, f of x is equal to constant c. So to keep it from being a constant function, we have that a can't be 1 and c can't be 0. We also have a restriction on our base that it can't be negative, and that's because if our base were negative, then there would be some values of x where we would have not a real number. So for example, if you had the function negative 5 to the power of x, then anytime x is representing a fraction that is represents an even root. So for example, if x were 1/2, you would have negative 5 to the power of a half, and power of a half, that's a square root. That would be square root of negative 5, which is, of course, that's not a real number. So to guard against that, to make sure that the output for f of x is always a real number, we're requiring ourselves that the domain, we're requiring ourselves that the base has to be larger than 0. And because of that, that means our domain for this function will be all real numbers. That no matter what value of x we put in, a to the power of x will be a real number, which means that all real numbers will work for the domain for any exponential function. Now, for graphs of exponential functions, there's two basic shapes, and it depends on what the base is. If the base is large, and by large I mean larger than 1, then it's a graph that's an increasing graph. You can see as we move from left to right, the graph is trending upwards. If you have a small value for a, between 0 and 1, then the graph would be a decreasing graph, one that goes downward as we go further to the right. And of course, a can't be equal to 1 because that was one of the restrictions that we had. For our base for an exponential function, it has to be positive and also not 1. One thing to know, though, that regardless of whether I have that a is between 0 and 1 or larger than 1, I always have the same 3 points that are on my graph. I have always the points 1, comma, whatever the base is. I always have the point 0, 1. And I always have the point negative 1, comma, 1 over whatever the base is. So as long as we can remember those 3 points, then we'll be able to come up with our graph of the exponential function a to the power of x without too much effort. Other things to note here, as I said, for an exponential function, the domain is all real numbers, but not surprisingly, the range is only positive values. And not a surprise because remember, a has to be something positive. And positive things raised to any power have to be positive. So not a surprise here that our range for this exponential function, y equals a to the x, would have to be only things that are positive. And as a nice consequence, if you are always positive, if you're always above the x-axis, then you can't cross the x-axis. There must not be any x-intercepts, and that's also true. I'm mentioning that because although it might look like it with my graph here, it looks like it's getting ready to cross the x-axis here or cross the x-axis there. Keep in mind that for these graphs, they do not cross the x-axis, that these exponential functions have no x-intercepts. They've got the one y-intercept, 0, 1, And they also have, and this is something that's maybe not obvious here on my drawings, a horizontal asymptote. And the horizontal asymptote is the line y equals 0. One thing to notice here is that the horizontal asymptote, unlike for rational functions, where it takes into effect on both sides of the graph, so when we graphed rational functions back in the last chapter, if you had a horizontal asymptote on the left side, you would have a horizontal asymptote on the right side as well, and that your graph might do whatever in the middle, but on the far left and far right, it would taper off to that horizontal asymptote. That's not true for exponential functions. Exponential functions, the horizontal asymptote only works or only takes into effect on one side. So depending on whether it's a graph of an exponential function that's an increasing one, in which case the horizontal asymptote is on the left side, or a decreasing function, in which case it's on the right side, there's only one side where we have a horizontal asymptote for our exponential functions. Okay, so now we're going to do some graphing via transformations, and I want to graph this function, y equals 3 times 2 to the x minus 1 minus 2. And before I graph any of the transformations, the basic graph is the graph of y equals 2 to the power of x. Once I've graphed that, I'll have 3 transformations to do. There's shifting things to the right by 1. There's stretching things vertically by a factor of 3. And then there is shifting everyone down by 2. So to start with, if I'm graphing my basic shape y equals 2 to the power of x, remember that it has as its points 1 comma whatever the base is, and here the base is 2, so we have the point 1 2, we have the point 0 1, and negative 1 comma 1 over whatever the base is, so negative 1 comma 1 half. And then on the left side, I've got that horizontal asymptote y equals 0, which I've drawn in as a dashed line. You can continue your dashed line all the way across if you want to, or not. Just keep in mind, of course, that the horizontal asymptote for this graph really only comes into effect on the far left of our graph. That on the far right, y equals 2 to the x will be increasing forever. So there we go. That's our basic shape, y equals 2 to the x. And now all we need to do is carry out our transformations. And so when we do our first transformation, which is shifting everyone to the right by 1, we're going to add 1 to all of our x values. So 2, 1 is now at the point 2, 2. 0, 1 is now at the point 1, 1. And negative 1 half is at the point 0, 1 half. The y equals 0, that horizontal asymptote, that should still be where it is, because if you take a horizontal line and move it to the left or move it to the right, it's the same horizontal line. So we should still have the horizontal asymptote y equals 0. So this is the graph of y equals 2 to the x minus 1. Okay, so now the next thing that I'll need to do is to stretch my graph vertically by multiplying all the y values by 3. That's my next transformation. So again, that's going to stretch my graph vertically. We're multiplying all the y values by positive 3. So the first point, which was the point originally 2, 2, I'm multiplying that y value by 3 to give me the point 2, 6. I had the point 1, 1. I've multiplied the y value by 3 to get me the point 1, 3. And I had 0, 1 half. And when I multiply that y value by 3, that gives me 3 halves, which is the same thing as 1.5. And the horizontal asymptote y equals 0 will still stay where it is as y equals 0. The only thing that would move a horizontal line would be if I were to shift it up or down. So when I have a vertical shift up or down, that will affect my horizontal asymptote. That will move it up and down along with the graph itself. But other than that, that's the only transformation that will affect my horizontal asymptote. So right now, shifting it to the right, stretching it vertically, that hasn't changed the location of my horizontal asymptote. And so this is the graph of y equals 3 times 2 to the x minus 1. And the last thing that we needed to do for our last transformation, that was a shift downwards by 2. That's the minus 2 at the very end. So subtracting 2 from every y value that we have. So the point 2, 6 shifts downward to the point 2, 4. 1, 3 shifts downward to the point 1, 1. And 0, 3 halves, that moves downward to the point 0, negative a half. And for our y equals 0, that got shifted downward by 2 to be the line y equals negative 2. And there we go. That's my graph of 3 times 2 to the x minus 1 minus 2. One thing again, just to clarify here, that although my graph might make it look like the might make it look like the graph is crossing that horizontal asymptote y equals negative 2, keep in mind that it is tapering off to that horizontal line y equals negative 2, but will not be crossing it. All right. One other thing to introduce here, and this is something that will play a role throughout the rest of this course, is a mathematical constant called Euler's constant. Euler was a famous German mathematician, and Euler's constant is a number that shows up in a bunch of locations in mathematics, in a bunch of applications. It shows up in exponential growth and decay. So if we're looking at, and we will look at later on, growing bacteria in a jar and looking at measuring how many bacteria are in the jar after a certain amount of time, as it turns out, this constant appears in that. There's a couple of ways that you can define this constant. And so the way that we're defining it is it's the number that you'll get when you let n, for this expression, get infinitely large. This expression is 1 plus 1 over n, the whole thing to the power of n. So it might not be obvious that this will actually turn out to be just a constant at the end. You might think, well, if n gets infinitely large, won't this necessarily get infinitely large? And you can try it out with your calculator, that when n is 1, you have a value of 2. And as you increase the value of n, the number gets a little bit bigger, but after a while, no matter how big you make n, the number does not change all that much. So for example, even here, just going from 1,000 to 10,000, there's not much of a change in the number that you get from 1 plus 1 over n to the power of n. Now, just like some of the other mathematical constants that we've seen, for example, pi, e is also an irrational number. Irrational meaning you cannot write it as a fraction. It has infinitely many decimal places, and those decimal places don't repeat. So that means it's not really possible for me to write the entire number e out, because just like in the same way it's impossible to write out the number pi. So whenever we're doing things involving pi, if we have an exact value, we would leave pi in our answer. Same sort of thing with e. A lot of times we'll be leaving e in our answer because e has infinitely many decimal places. You can't actually write it out without having to round it off. Even this, which I've written here, I've written the first 10 or so decimal places out. That's still only an approximate value. This is not the exact value for e. So there may be some times where you'll need to find what the approximate value for e is, and that we can use our calculator to help us out. If you're taking a look at your calculator, the Sharp EL531, you can see that right here above this button that we have, you can see that as a second function you have e to the power of x. And so if you wanted to use this to calculate e to some power, all you would have to enter is second function, e to the power of x, and then just enter whichever power you're interested in. So for example, e to the power of -1, I would then enter -1, and then equals. One thing to notice here is that if you're using the exponential function, e to the power of x, you do not have to use the exponent button to raise something to a power. So for example, if I were looking for e to the power of -2, I would only have to enter second function, e to the power of, and then -2. All right, so that means for a little bit of calculation work that we might have to do here, if you're looking at finding approximate values for things, so e to the power of -1, so second function, e to the power of -1, and you'd find that that's 0.36787, so approximately 0.3679. E to the power of 1, that's second function, e to the power of, and then 1, and that's 2.17828, and so on, or for 4 decimal places, 2.7183. E squared, so e to the power of 2, second function, e to the power of, and then 2, that's 7.38905, and so on. So approximately 7.3891. So now we're going to graph a transformed exponential function. And as I said, although we might sometimes need to find the approximate values for e to some power of x, for the most part, we're going to leave things in exact values only, which means that, for example, when I do the basic graph of y equals e to the x, we know that there's the 3 points, 1 comma the base, 0 comma 1, -1 comma 1 over the base, and those will be how I label my points. So for example, the point 1e, I'll label it as 1e. I will not be labeling it as 1 comma 2.718. 2.718 is the approximate value for e. It's close to it, but remember e has infinitely many decimal places, so it's actually not possible to write out e in its entirety. That's why we have the symbol for it. So I'm going to first start off with graphing my basic shape here. I have my points 1e. E is about 2.718, so roughly here is where it is. You can use your calculator to figure out roughly where the point needs to be, but when I label it, I'll need to label it with exact values only. The y-intercept is the point 0, 1, and then I have the point -1, comma 1 over e. 1 over e, or e to the power of -1, that's about 0.367, so somewhere around there. Of course, for my horizontal asymptote that I'll have will be the line y equals 0. And there we go. There's my basic shape for y equals e to the x. All right, so now let's get into the transformations. There's two transformations that we'll need to do here. And I'm going to just rewrite this so the transformation is maybe a little bit more obvious. The e to the power of x over 3, you could really think of that as e to the power of 1/3 times x. So what that means is, of course, when we have a number multiplied by the x, that is a horizontal stretch or compression. And we'll need to remember that what will happen here is instead of multiplying every x value by 1/3, we'll be doing the opposite. We'll be dividing every x value by 1/3, which is the same thing as multiplying every x value by 3. So that instead of the point 1e, we'll multiply that y value by 3 and have the point 3e. 0, 1, multiplying the x-coordinate by 3 still leaves it as 0, 1. And -1, comma 1 over e, when I multiply that x value by 3, I get the point -3, 1 over e. The horizontal asymptote won't have moved because, of course, if you're stretching things horizontally, the horizontal asymptote will stay where it is. It would only be a vertical shift. If we shifted things up or down, that would move a horizontal line. But we haven't shifted anything up or down yet, so that horizontal asymptote will stay where it is as the line y equals 0. And then finally, we have the last transformation that we want to carry out is shifting everybody upwards by 2. And so for that, we're going to add 2 to every y value. That also means that since we're shifting everybody upwards by 2, that this horizontal asymptote will also shift upwards by 2. So when I graph it, I'm going to start by graphing my points and my horizontal asymptote after shifting everyone upward by 2. The horizontal asymptote was y equals 0, and we're going to shift it upwards by 2 to make the line y equals 2. And now for my points. I had the point 0, 1, which when I shifted upwards by 2, that's the point 0, 3. The other 2 points I have to be a little bit careful about. So originally I had the point 3, comma e. That was originally my point here, and I'm going to shift it upwards by 2. And so when I shift it upwards by 2, I do that by adding 2 to the y value. So the y value would be e plus 2. That would be the exact way for me to write the y coordinate here. If you wanted to know approximately what is e plus 2, you can use your calculator and find out that it's about 4.7. So I've put it a little bit above 4. But again, we're not going to be putting in decimal values here. We're going to be writing exact values only. Same thing for my other point, -3, comma 1 over e. That would be when I shift it upwards by 2, -3, comma 1 over e plus 2. That's how I would write that. As a number, you can find out that that's about 2.37, so a little bit above 2. So I've got it roughly in the right spot. But as far as writing out its coordinates, we're writing them out in exact values only, so that's as 1 over e plus 2. And the only thing left for me to do is just to label my graphs. So the one graph, 2 plus e to the power of x over 3. And this one I didn't label. Y equals e to the power of x over 3. There we go. So now I've got my graphs all nicely labeled and with all the important points plotted, as well as the horizontal asymptote also plotted.